Now we're going to look at the general multiplication rule and the mathematical test for independence. So the general multiplication rule, all it is an algebraic manipulation from the conditional probability rule. So if you go back and look at that, you'll notice that these look very, it's like, oh, wait, this is pretty similar to what we've done. Now, before, so I'd suggest pausing, going back and taking a peek at it. Probability of two events, E and F occurring, equals the probability of the conditional of F given E times the probability of E, and it also has to equal the probability of E given F times the probability of F. Now, like I said, these are just algebraic manipulation from the conditional probability rule. So we're going to use this. Before we started with that, if they were independent, we could do that multiplication rule. But now we're saying we don't know if they're independent or not. So to find the probability of E and F without knowing if they are independent, we're going to need to use these instead. Now to check mathematically for independence, events E and F are independent if the probability of F given E is the same thing as the unconditional probability of F. Also, the events E and F are independent if the probability of E given F is the same as the probability of E. Once again, the unconditional probability. But this is an or. Okay, you don't have to test both of these. You just need to test one to check for independence. Remember, this is the unconditional probability here. When we test mathematically, numerically, in this class, if the numbers are not exact, we are going to say that they are not independent. So if the two numbers, and we'll show an example a little bit later, that if we'll say they're not independent unless the probabilities are exactly equal. In real life, it would be very, very unusual to find the probabilities exactly equal. What we do is in practice, we're going to look at independence. We're going to assume independence, excuse me, and then check the sample to see if we're close when we do this calculation and to see if independence makes sense in the way we designed the study. But for right now, we're going to focus on doing that mathematical calculation. So we're going to look more at the payment methods. This is some more information from that poll in June of 2011. Now they found that 74% of the people had a debit card, 71% had a credit card, and 53% had both. Organize the information in a contingency table and a Venn diagram. The Venn diagram, remember, I'm not going to require you to do them, but I do want you to be familiar with them and comfortable. So the Venn diagram I will show you. I was just pausing the video for a moment and see if you can come up with the contingency table that would be for this information that's given in example 4.3, and then come back and check your answer. Before I go on, I want to show, this is basically how I set it up. They can be very quick to set up. I said C is for credit card, so either have one or you don't. D is for debit card, either have a debit card or you don't. Now, this information that I have filled in so far is right from the information that was given to us. So the 71% have a credit card. You see that there, 0.71. Remember, the probabilities on either side, or either in the column or in the row, have to total to 1. To be a valid probability model, everything has to be accounted for. Now here, what rule would I use to fill in the rest of these boxes? Well, hopefully you think, well, she's just going to use that complement rule. They have to add down to total 0.71, have to add across to be 0.74, have to add down once again, and then these just all fall out. The one nice thing is if I add down, I'm like, okay, I add down here, got 0.29. I can double check myself and say, oh, they added across to get 0.26. Perfect. Now, what if instead I was doing this as a Venn diagram? Well, do these two circles intersect? Can people have both? And the answer is yes. Remember, we don't worry too much about it being exact, just we're going to say they intersect. Here's going to be the debit card, and here's going to be the credit card. We know that the probability of having a debit card is 0.74. So that's in this circle. And a credit card is 0.71. We know they overlap here, debit and credit card. This has to be 0.53. Sorry, that got a little small there. So this has to be 0.53. Now, by default, do we know if this total circle has to be 0.74, what has to be the area in here? And I'm going to change colors. You're like, oh, right, it has to be 0.21 because 0.21 plus the 0.53 has to add up to the 0.74. This in between here, just to remind you, is the probability of D and C. And likewise, this has to be 0.18. Two different ways of displaying the information, but the information is the same in both. Determine the probability that if a consumer has a credit card, they will also have a debit card. Ooh, do I hear a condition? Yes. So the probability that if they have a credit card, they also have a debit card. Well, okay, there are a couple different ways I could go about this. I could say, well, I can use my contingency table, which is honestly what I would generally do, and say, well, what percentage have a credit card, or what's the probability to have a credit card? 0.71. Debit and credit card has to be that 0.53 because this is debit and credit is right in here. And I get 0.746. Did I even need to complete part 1 to do part 2? No, I could have used that conditional probability, that rule, and just done probability of D and C, which is the 0.53 divided by the probability of C. Are having a credit card and a debit card independent events, and how are you deciding? Well, I just populated. Yeah, I just calculated the probability of a debit card given a credit card, and I got 0.746. Now, for these to be independent, the conditional probability would have to equal the unconditional probability. But I get that that's 0.74. That's what we're told. Are these two the same? No, they are not equal. They're not exactly equal, and so they're not independent. And that makes sense to me that one could influence whether you have the other. Are having a credit and a debit card mutually exclusive? You're like, well, I just checked independence. Right, but remember, mutually exclusive and independence are different. How are you deciding? Mutually exclusive, it means that if you have one, you don't have the other. But we see, obviously, no, you can have a debit card and a credit card. We also can see by the probabilities that we'd have a debit and a credit card is 0.53, which is not the same as 0. So they are not mutually exclusive events.